Here, screen. All right, name these compounds. What? What is it?
What's in?
She just looked at me all kinds of.
I said Maryland.
Yeah.
I didn't know it.
Oh my gosh, you guys.
Orthodox? Like an Orthodox Jew?
What's that one? Paradox. Oh my gosh. What's that one? Everybody always does that.
Pyramid. Ah, got it.
Oh my gosh, you guys. All right, now name this one for real. Oh, funny. I know. Everybody starts looking at the break table. What's MD? What's MD? It's 101. It's Mendelevium. It's named for the guy who made periodic table, I think. But nobody thinks Dr. Wasson would never capitalize letters. Never do that. All right, I guess I should. 18, maybe? About 18? All right, I got 5 more. Make a guess. Because a guess is better than none. Just breathe. Just breathe, Tanner. What your shirt says.
Oh, yeah.
Did you see that movie, 5 Feet Apart?
I'm so good.
Oh my gosh. My husband picked it for his birthday. So we go in, we're all bawling, all of us. Anyway, he made a picture that said just breathe. That reminds me of. Okay. How'd we do? Okay, so first of all, you have to use what? Numbers, right? Because it is 3, right? If you have 3 or more, you can't use ortho, meta, and para. Okay, so we've cut out those. Okay. All right, what is the base name for discovery?
Irene.
Yes, good. Okay, so what does that tell you? Which carbon is number 1, right? Okay, now how are you going to alphabetize? Clockwise or counterclockwise? Clockwise, because this is what is the name of that group? T-butoxy. What's the name of this group? Fluoro. You were going to get the same number. That's FL. Yeah, kind of sad looking. Okay, you're going to get the same number, 135, 135, right? So you pick it by alphabetical. And you remember the alphabetical rules? The B. So it's going to be this way. Okay, so it's C. Okay, hope you review all that. Chapter 17, we're going to do some reactions. Okay, electrophilic aromatic substitution is the basic reaction we're going to get through before we get to the test, okay? This involves an electrophile substituting for one of the hydrogens attached to the benzene ring. So what is an electrophile, first of all? What's an electrophile? What is electrophile? Electron loving, okay? So electrophiles are electron loving. So what does that tell you about them? They are typically what charge? Positive. Seriously, I circled it 5 times. Okay, they're typically positive. They don't have to be positive, but they're typically positive. You'll see as we go. They are either going to be positive or delta positive. Remember what the little delta means? Okay, so, and we are doing a substitution on an aromatic ring. Okay, so all we have on this benzene are 6 lovely hydrogens. Okay, and so what's going to happen is you have to have something. Remember that being aromatic is super stable. That's the driving force for the whole reaction. Being aromatic is super stable. Benzene will not react with an electrophile unless it is super positive. Okay, because what will happen is this will react with the E. You may or may not have a leaving group. It depends on what's there. Okay, and you end up getting an E replacing for your H. Notice that the H is gone now. Remember that there is 1 hydrogen on each one of these carbons, but there's no hydrogen on that one. Okay? So what happens is we disrupt the aromaticity by adding our electrophile, and we get an intermediate that looks like that. Okay? Notice that we have a plus charge, but is stabilized by the other electrons in the benzene ring. Okay? Now I'm going to lose a hydrogen to end up with this. Which hydrogen is the one that got removed? Which one? The one that's on the same carbon as the E. It's really important to see that. People like to forget where the hydrogens are because we're drawing sticks. So if you're drawing a stick, draw some of them in, maybe, if that helps keep you on the straight and narrow. Okay, so that's general. That's general. Okay, so now what we're going to do is we're going to make different things that will go in there. Okay, oh, well, all right, we're going to do this first. All right, so here is our benzene ring going for the E+. Now, when I draw these mechanisms, I am not going to use the circle in my benzene. If we're just drawing the products, fine. But when you're drawing the mechanisms, it helps you keep track of the electrons. Okay, to draw the double, single, double, single, double, single. Do one of the calculate formulas. Pick a double bond. It doesn't matter which one, right? They're all the same. Okay, so look what we got. We got this. This thing lost aromaticity. But remember, being aromatic is super stable. So what we're going to do is get it back. Okay, so something is going to be a base and remove this proton. These electrons go down there, and look what you did. You got back the aromaticity. Okay, and you got HY, whatever Y is. We're going to get specific in a minute. Okay, this weird thing that says lost aromaticity has several names. Benzenonium ion. Is the one I tend to use. Okay, is the one I tend to use. But I've seen different ones in different books, and I don't know if there's a rhyme or reason. Like cyclohexadienyl cation. Well, okay, that is kind of what it is. So I don't know. So there's multiple things you can use. I'll use benzoate ion probably. Okay? Are you with me so far? Okay, I know it's a new thing. Okay, this little benzoate ion. Okay, see, look, I've got arene ion, cyclohexadienyl cation, benzoate ion. I don't know if one is like the accepted one or what. I think your book must have used the arene ion. That's why the benzoate ion is in parentheses. Okay, so what we're going to do is we're going to draw resonance forms for it. Okay, so how do you figure out where do you going to start? What can move when you draw resonance? Nothing. Lone pairs and pi bonds, right? What have we got? Pi bonds, okay? So I'm going to take this pi bond, and where am I going to go? I'm going to go from, this is your high electron density, the plus is your low, so I'm going to go from here to there. Doesn't matter if you drew your arrow on the outside of the benzene ring. Like if you drew it that way, doesn't matter. Okay, don't get hung up on that. All right, so now I'm going to draw what didn't change. Did I do anything with this E or this H or this H? No, they're all still there. Did I do anything with this double bond in the bottom right? No, it's still there. Okay, so what I did do was I took those electrons and put them up there. So what do I have up here in my upper left? I have a double bond. And what about this carbon? Remember, it has one hydrogen on it. It is now positive. Are you positive? Don't get choked up. Not worth it. Everybody's coughing. All right, so how are we going to get another one? Yeah, I'm going to take this double bond and I'm going to move it there. Okay, so I'm going to do it the same way, draw what didn't change. Okay, I didn't do anything with the red double bond. It's still there, right? Okay, what about the E and the H on that carbon? Still there. Remember, we're doing resonance forms. Okay, when we do resonance forms, we don't move the atoms. We only move electrons. All right, so bottom left, what do I have now? Double bond, and this carbon, I'll draw that H in, has now become positive. Notice we're not drawing arrows showing the plus moving around. The carbons are becoming positive because they lost electron density. Remember, your arrows mean movement of electron density. I feel like it's been a while since we did that. I don't know why. It may not feel that long to you. Okay. All right, so here are the basic electrophilic aromatic substitution reactions. Notice I've got reaction, reagents, electrophile, and what the product is. Okay, so here's the first one. The first one that we're going to talk about is halogenation. So what do you think we're going to put on the benzene ring? Halogen. Y'all are so good. Okay, the reagents typically are X2 in FeX3. Okay, so if you used bromine, you would use Br2 and FeBr. If you use chlorine, you would use Cl2 and FeCl3. Okay, the fluorine and the iodine, well, we'll talk about that, but yeah, it's pretty much going to be chlorine bromine. Now look at this over here. This is your electrophile. Isn't that weird? Okay, Fe, oops, I lost the E. FeX3, so here's an example, is FeCl3, okay, is a Lewis acid. What do you remember about those? Okay, when you draw a Lewis structure, you have to show all the, what? When you draw a Lewis structure, when I say draw a Lewis structure for this compound, you have to show all the bonds and Lone pairs, all the electrons. Okay, it's the same guy. So Lewis acid has to do with electron pairs. Bronsted-Lowry is the H plus. Okay, so electron pairs. So a Lewis acid is an electron pair what? Acceptor. Remember, H plus and OH minus are acids and bases in every definition. So you can use H plus to figure it out. Is H plus going to accept electrons or donate them? It ain't got any. So it's got to accept them, right? Okay, so a Lewis acid is an electron pair acceptor. Where am I going to get electron pairs? Any idea? From a lone pair on the halogens, okay? So if you're doing this, you would do the chlorine in FeCl3, the bromine in FeBr3. Okay, they always match. Notice that if I use the chlorine, what am I going to put on here? A chlorine. Don't be putting bromine on. Okay? All right. Next one. Nitration. Nitration uses HNO3 and H2SO4. Okay, what's HNO3 called? Nitric acid. Okay, it's one that we haven't used very much this semester. Okay, our electrophile is NO2 plus. Looky there. Here, since we're into lone pairs. Okay, don't worry, we're going to make it. We're going to go over it. Okay, notice what we did put on the benzene ring. An NO who? An NO2. Okay, not an NO3. Okay, it's an NO2. It's from the electrophile. Okay, next one. Sulfonation. Sulfonation uses SO3 and H2SO4. And look what we put on the ring. SO3H. Ooh, all right. So, first of all, that looks like this. Remember, sulfur breaks the octet rule just to confuse students. That's the only reason it did it. You didn't know that, did you? Phosphorus too. That's the only reason they do it. Make life hard for general chemistry students who have to draw all those Lewis structures. Okay, now look at what my electrophile is. SO3. There isn't a plus on it. Like, that had a plus, that had a plus, one done got a plus. Has to do with the structure of SO3. Okay, we'll talk about it. All right, now this one is the Friedel-Crafts acylation. Acylation, okay? We are going to, what is a carbonyl Cl molecule? Carbonyl Cl. We heard of a acid halide? Yeah, we kind of mentioned that a little bit. Okay, and look at this little thing, AlCl3. Guess what that is? That's another one of these Lewis acids. Okay, so we're going to use an acid halide and AlCl3. Okay, we'll just use the chlorine. You could do it with the bromines, but okay. Now look at your electrophile. I feel like it's too small. That is called an acylium ion. I didn't tell you all the other names. Okay, that's all right. We'll go over each one in turn. Okay, now I want you to notice what we made. The benzene is attached to what atom in the acylium ion? The carbon, not the oxygen. Yeah, so you can go out and give the O back its lone pair. Okay, everybody see that? That's what we're putting on. That is referred to as an acyl group. An acyl group is a carbonyl and an R. Okay, that's an acyl group. What's an alkyl group? Just an R. Okay, just like methyl isopropyl. Those are all alkyl groups, okay? Did a reaction in lab that was electrophilic aromatic substitution. So you know all about it already, right? This is just total review, right? Okay. All right, here's the one that you did in lab. Friedel-Crafts alkylation. We're going to use RCl plus AlCl3. And the R that y'all did in lab was a TBO group. Okay? Notice what we got here. We have a carbocation with AlCl4 minus as the counter ion. Okay, and what did we put on that old benzene ring? The R. When you did it, you put on how many R groups? 2, didn't you? Well, there's a special reason. Okay, did you go over that? We talk about activating. Okay, well, I will. It's okay. What? He mentioned it. Okay. All right. So halogenation is the first one we're going to tackle. Okay. I drew that 1H in so that you would see that it is no longer there in the product. Okay. These are the Lewis acid catalysts that you can use. FeX3 and AlX3. Okay. Typically, FeBr3 gets made in C2. What does that mean, in C2? Within the within the reaction mixture. Okay, so if you take bromine and you add iron to it, or you add bromine to the iron, you get FeBr3 formed there. Okay, sometimes it's easier to just make it use it rather than have to try to clean it up or purify something that you bought 20 years ago. Yeah. Okay, now here's your electrophile. Okay, the iron becomes negative when it grabs that lone pair from the bromine. Notice that the bromine in the middle is plus, right? Because it should only have one bond. It has 2 bonds. Okay. If you want to do iodination, you can get I plus from I2 in nitric acid. Nitric acid is like the nastiest of all the big acids that you talk about. Sulfuric, phosphoric, hydrochloric, okay? Nitric is nasty. I had a friend in college, and he was doing something in the lab, and he poured nitric acid into one of those burettes. Concentrated nitric acid. Guess what he did not use? 2 things. He didn't wear gloves, and he didn't use a funnel. You know how narrow those tops are? Oh my gosh, yeah. Well, needless to say, he spilled it. It got on his hands because he was holding it with one hand. Nobody understood that. Anyway, it was a mess. His fingernails. It's like scary stuff. I hate nitric acid. I don't even like it. Yeah. Yeah, it's nasty stuff. So if you ever have to dilute nitric acid for a reagent or something, just be super careful. It's bad. Bad, bad. All right. We got that far. Okay, so the first thing we're going to do is we're going to make the electrophile. In order to make that, one of these lone pairs goes to the Fe. Remember what the arrow means. Movement of electrons. Okay, and so now the Fe is negative and the bromine is positive. Okay, so we made our electrophile. It's only one step. Some of them are only one step to make them. Some of them you don't even make. All right, so now I'm going to take my benzene. If you do not make the electrophile, if you just put benzene and bromine together, would not get a reaction. You have to have that acid, or Lewis acid catalyst, excuse me, in order to get this to have a plus in it. Now, I want you to notice that every carbon on the benzene has a hydrogen. So I'm drawing them in up here so you don't forget them. Okay, and then we've got our little arrow. I picked that double bond. It's going to go there, and then those electrons go back to the Br. Why doesn't it go to the one in the middle? If it went to the one in the middle, you would not alleviate the plus charge, right? You would have a benzene ring with a bromine attached to an FeBr3, and the bromine would still be plus. The only way you can take care of that is to go next door, okay, and get that one and give those electrons there. Okay, so this is our new bond right here, okay? And your FeBr4 minus is actually going to be your base. Okay, that base is going to remove the offending proton, the one that's on the carbon that the bromine is on, not this one. Okay, that one's still there. And then those electrons in the CH bond go there, and you get back your aromaticity. See, this hydrogen up there is still there. When this grabs the proton, it falls apart and becomes HBr and FeBr. So your Lewis acid is a catalyst. It is regenerated. Okay? You probably use T-butyl chloride and aluminum trichloride, right, for your catalyst. That's pretty typical. Did it work good? Did you get a good yield? Do you feel like you got a lot of stuff? Okay, good. Almost 2 grains. Cool. Cool. Well, we've had years where we didn't get so much. The aluminum chloride will pick up moisture in the air and become bad, and it's like a pain in the butt. Yeah. And we cried. All right. What is the name of the mechanism for the reaction below? Trying to give you some points here. It's 18, right? Yay! Okay, so if the question asks you what is the name of the mechanism, make sure you write it down. Okay, nitration, we're going to add what to our benzene ring? NO2. NO2. Okay, let's see. Make it show up. There we go. There's our NO2. Okay, nitronium ion is the electrophile. This is what the nitronium ion looks like. Okay, so the first thing we're going to have to do is make that, because the reaction won't go unless you have that present. Okay, that has to be made. All right, everybody's drawing little pictures. Okay, notice what happened to this hydrogen that I can't seem to circle. Let's try again. What happened to that hydrogen? Where is it? Gone. Out of here. Okay? Notice that even though we had H2SO4 in there, we didn't put a sulfur on there. We put the nitro on there. Okay, so the first thing we're going to do is make the electrophile. So we're going to protonate the nitric acid. Okay, so y'all remember how to draw all these acids, right? Oh. Do you remember that that's what nitric acid looked like? Yeah, totally. Everybody says that. Oh, yeah. Dr. Smith didn't beat that into you? Okay. All right, there's nitric acid. See, now they did the little shorthand, just wrote the NO2. Notice that the nitrogen has 8 electrons around it. The oxygens all have 8 electrons around them, but one oxygen's negative and the nitrogen is positive. My electron's missing. There we go. Okay, all right, so what we're going to do first is we are going to protonate NO. Why don't we protonate the O that's negative? Yeah, we can, but you don't get anywhere. Okay, so until you protonate the OHO, you won't get anywhere. All right, so there's your sulfuric acid. I won't even draw that out for you. I don't care. All right, and so we protonate that, and that's going to fall apart. I like, because I think it shows it better, to draw it like this. Okay, so this goes there and that goes there. I guess I'll do it like that. So that you end up getting your nitronium ion. Because that doesn't show you the, I guess I should just let them blank and just drawn it in. Okay, so it looks like this. Notice that we don't have a minus to offset the plus anymore. The nitronium ion is positive. So it's your nucleophile. Okay, and I'll fix this so that it won't be there in your little final slides. Okay, everybody got that? So we protonate and then we lose water. Okay, so now what is our benzene ring going to attack? It's going to attack the nitronium ion. Okay, I'm going to rewrite it again. Maybe. Apparently. I'm just going to scribble that out. Putting in my lone pairs for you. Okay, and the N is plus. Okay, so watch what's going to happen. The benzene ring, one of the electrons pairs is going to go to the N that's positive, and then we're going to go out to the N. Okay, we're not going to break the octet rule on nitrogen. It's still going to have its octet rule. Okay, so that will give us that. Now, what do we have in there that can be our base? What's in our reaction mixture? What did we make up here? Little H2O, right? We got a little H2O action. Okay, so this will be, I should have just drew the whole thing. I think it's messy. So your lone pair here is going to grab that H, and that goes down to regenerate your aromaticity. Oh, I wrote B equals water, didn't I? Okay, and then I want you to see that the hydrogen on that carbon is gone, the one where the nitro is, and that the structure looks like this. Whoops, that's what I want. So we're going to have N double bond O, O plus minus. This is what a nitro group looks like. It has this separation of charge in the nitro. Okay, so because of that, it tends to make things to be extremely crystalline, because you've got that ionic stuff going on, and very, very much soluble in inorganic things, or in things that are highly polar, like alcohols and stuff. Okay, even more soluble in water. Okay. Okay, how do you feel about them? Do you see how this mechanism is the same as the last one? Okay, the only thing that's different is making the electrophiles, but all the mechanisms are the same. We're going to take our benzene ring, we're going to grab our electrophile and lose aromaticity, and then we're going to get it back. And that's the basic mechanism for everything. So isn't that nice? Okay, little consistency for you. Okay. Okay, now I want to show you. Here's your benzononium ion. See, I can't not say that. Okay, and then here's this. How much time we got? Oh, we got 2 minutes. We can do these in 2 minutes. Dang, I had a couple more questions for you. That's all right. We'll do them the next time. Okay, so draw me the resonance forms for this. For the benzononium ion. Okay, so I'm just going to write NO2 now. I wrote it out once. Okay, so what are you going to do first?
You're going to move the double bond.
Which one?
The first. Yeah.
Okay, so between these two carbons, I now have a,
Double bond.
okay, and this carbon is, what about over here?
You got a double bond.
I still have that double bond that I had to begin with. We didn't touch it, right? Okay, draw me the next resonance form.
You move the second double bond.
Okay, so I'm going to take this double bond and I'm going to go here. Remember, we're pushing electrons. Pushing electrons. Okay, so what is that going to be? All right, so I'm going to draw what didn't change. Okay.
Then the double bond's over there and that carbon also.
Okay, so my double bond is here,
No.
here, and this carbon has become positive. Are you positive? If you need to, figure it out. Remember, there's an H on there. The normal valence of carbon is 4 minus. How many shared electrons are there? 6. Half of 6 is 3. How many alone pairs are on there? 0. There's your chart. Okay? All right. We'll do more on Friday.